Okay, let's continue our journey in the small intestine. I want to bring up, before we move on to the small intestine, this is actually related to the small intestine, but I want to add a little bit more to what Dr. Shuttleworth was talking about with gastric inhibition and GIP, gastric inhibiting peptide. What gastric inhibiting peptide is designed to do is it's designed to feed back on the stomach. So how does GIP come about? One of the primary mechanisms of GIP is components of our diet recognition in the small intestine. So this is something that we've seen before. Material gets into the small intestine and it's going to activate the open endocrine cells for signaling to secrete the hormone. So what we see with GIP, there's our stomach. Nice drawing, huh? Okay, so as material's coming out into the small intestine, in the duodenum, the duodenum is not necessarily, as Dr. Shuttleworth pointed out, it's not involved in a whole lot of absorption. Because what the duodenum is for mixing all of those enzymes that we saw coming out of the pancreas with the bile and starting to get everything mixed up with the stomach chyme coming out through the pyloric sphincter. So as we project this material down into the ileum, what we're going to need to sense is glucose. Of course, glucose is our primary energy source. The glucose is coming from our starch digestion, which is the topic of what we'll talk about in a few minutes. But what these cells are going to do when they sense glucose is that they are going to put GIP into the bloodstream. GIP traditionally stands for gastric inhibitory peptide. Now, the purpose of this is the same concept as CCK. So up here in the duodenum, we are recognizing, as Dr. Shuttleworth said, there is kind of a gradient effect on sensing. It does sense the I-cell system, does sense the peptides and amino acids, but it is primarily fatty acids. And this is going to be causing the secretion of CCK. Now, this is sensing the fact that we have a lot of fat coming out. Fat is very difficult to digest. Remember, fat is a chemistry problem in the body. So we have to get the fat processed with the bile to emulsify it first. So what we want to do is feed back and inhibit on gastric emptying. GIP is going to do the same thing. This is going to inhibit gastric emptying. Now, this is because if we have a sense of a high carbohydrate content in our intestinal lumen, we want to give our intestines, which we're going to see today, the principle of uptake. So we need to be able to take this glucose up. All of our uptake mechanisms in our intestine are saturable. So remember the principle of saturation. You have so many molecules, receptors, transporters that can take material up, and if you overwhelm it with ligand or substrate, you can saturate the system and lose some of our necessary molecules. So what's happening is we have GIP feeding back and slowing the emptying of the stomach. Now, there's another name you need to be aware of GIP. Minutes later, it's called glucagon-like insulinotropic peptide. This is the more common name for it, for GIP. And what this now does is it actually stimulates, this GIP is a positive stimulator of insulin secretion. And we're going to talk about the whole insulin secretion process next week. But GIP, what it does is it slows the stomach emptying, giving the intestine time to take up the glucose, and it's also priming the islet cells in the pancreas, saying, we got a lot of glucose in the intestine that we're absorbing, start secreting insulin. Okay, so it's kind of forming a dual function. Okay, so that's the dual nature of GIP.
Does this mean if you have a lot of glucose or carbs/dumping in the intestine that you can also have hypoglycemia?
Yes, exactly. Because this is where, so the question is if you've got a lot of dumping and you've got a lot of glucose coming in, can you induce a hypoglycemic state? Yeah, because you've got GIP increasing its concentration in the blood, which is going to give that pulse of insulin secretion. And if the glucose has not been properly absorbed and circulating in the blood, you can have a hypoglycemic episode. Sure. Okay, so that's just a little bit of an addition to try to pull that together. Now, the other thing that I want to mention is go back to our water control and secretions in the intestine. So Dr. Shuttleworth talked about the enteric nervous system, that enteric reflex, where you've got contraction behind, relaxation in front, law of the intestines. What that is going to do is it's going to secrete VIP as part of the relaxation. Well, when that is happening in your gut, the other thing that you want in your gut is a lot of water to go into the gut, because that water is going to be essential to dilute out the chyme that's moving through, to give you a little bit more of a bolus for that segmentation contraction. And you want to have sufficient water in there for the enzymes to perform their digestive function. So this is where VIP is coming from. It's coming from these enterics. So the VIP is serving three functions. It's causing relaxation in the smooth muscle to allow for peristalsis. It's serving as a ligand to activate the cyclic AMP pathway through GS, which is now going to activate protein kinase A that will phosphorylate the chloride channel, CFTR, and now the chloride is allowed to flow out from the cell into the lumen of the gut. Sodium follows, and of course, water will chase those ions. So that's the second coordinated function of VIP. The other important feature of VIP is, where does this water come from? There's only so much volume of water in the intestinal tissues, so it's going to have to come from our plumbing, our bloodstream. And so the blood flowing down here is going to be the major source of the ions and the water. And so that means that the VIP, this signal, must also cause vasodilation. So that connects the VIP from the enterics with our water secretion and where the water and ions are coming from in the vasodilation. So it's a nice, beautiful, coordinated response. Okay, so what I want to do before we start talking about the secretions and the function in the small intestine is bring your attention to this picture. You're going to see this picture so much over the next several weeks that you are going to grow to hate it. This is how we are going to structure our entire metabolism and nutrition portion of the block. What we have here is we have glucose plasma levels on the y-axis. We have non-esterified fatty acid plasma levels on the other y-axis. And on the x-axis, we have time. And what we're going to do is we're going to continue our theme of GI, talking about consumption of food, absorption of food today, digestion, absorption of food, and then blood levels of these components that we're going to absorb, and then we're going to take that into metabolism and see how the metabolism is controlled by the absorption of our food products, our fuel molecules. So for now, I'll go over this after your exam on Monday in detail, how to interpret this picture. But for now, what we need to think about is right here. This is where we're at today. What this represents is that this line here, this homeostasis, over time we're not seeing any changes in blood glucose. But this point here represents mealtime. And mealtime, when we're talking about metabolism, is not when you put the food in your mouth. What it's talking about is post-absorption. So once this fuel products and food gets inside our body, then metabolism really begins. So today we're going to be talking about here and what causes that increase of that slope so that we increase the amount of glucose in our plasma. And so that's where we're going to focus today, the digestion of our food products and then the absorption and uptake of our food. Okay, so let's start with the biggest food product that we consume. Carbohydrates. So our carbohydrates, we have three primary carbohydrates. We have first starch. And remember, starch is a polymer of glucose. Our polymerines, we have these hexoses linked in a linear fashion by our alpha 1,4 linkage. Now, starch is very, very dense as far as calorie and energies. So what we're also going to have, besides these glucose polymers, we're going to take these glucose polymers and we're going to attach them on top of each other to form an alpha 1,6 linkage. So then what we have is a very, very long polymer of glucose attached covalently to another long polymer of glucose. Now we can keep stacking these polymers on top of each other by forming these alpha 1,6 linkages. Now, the reason I bring this up to your attention is that when we have a polymer of glucose stacked up, linked up by these alpha 1,6 linkages, the common name for it is starch. There's still a persistence of the old nomenclature. So a linear form of the glucose can also be called amylose. And this is where the enzyme amylase came from, because amylase is the enzyme that digests amylose. When we look at the branch of these long polymers with this alpha 1,6 linkage, that can be called amylopectin. And that simply represents we have polymers of glucose that are linked together in a branch structure of an alpha 1,4. Now this is going to have some very, very profound differences on how these sugars are processed. So the other one is sucrose. We looked at sucrose before. This is a disaccharide because we just have simply two sugars linked together, glucose and fructose. And then the other carbohydrate in our diet, of course, is lactose, which is also a disaccharide of galactose and glucose. So these three carbohydrates, the starch, sucrose, and lactose, are the primary carbohydrates that we have to digest and absorb into our body. Okay? Now, let's start out with lactose. Lactose is the easiest one. So I have the pattern of lactose digestion here, drawn up as lactose intolerance. because this is really a common problem. So lactose is that disaccharide of glucose and galactose. We take this in, and under normal circumstances, we can digest this. And we can digest this primarily because we have, where's that enzyme? Oh, it's not drawn in this. We have, oh, here we are. The brush border, that microvilli structure of the epithelial cells, has the enzyme lactase. Now, we've been talking about the pancreas as the primary organ for synthesizing and secreting all of the enzymes that we need for digestion. There's a couple of important ones that are actually located as transmembrane proteins that face the apical surface so that they are exposed to the lumen of the intestine. One of them is lactase. And so the principle of lactase is it's going to hydrolyze the galactose and glucose, releasing those two sugars as monomers. Now, everything is all happy and hunky-dory until you encounter a patient that is lactase deficient. Now, how lactase deficiency comes about, I still haven't seen much in the literature. Because many times children have lactase, but the expression of this enzyme declines and decreases as people age. I put this number up here of populations that suffer from lactase deficiency, just to kind of give you a little bit of demographics on what you'd be facing with patient populations. But what is the problem with lactase indeficiency? Lactose intolerance? Well, we have these wonderful things down here. Where are they? There it is. Bacterial fermentation. So the very fact that you may have the absence of the enzyme lactase, the bacteria actually are very happy to contribute their lactase into the gut. What that's going to do is they're going to be able to digest the galactose, glucose monomers together. The bacteria now use this for energy production. Fermentation. So what happens in the gut? We have a very anaerobic environment in the gut, which means that there is reduced oxygen in the gut. So that means that bacteria are still going to perform their biochemistry. They're still going to oxidize these sugars to generate energy. They're still going to go through the electron transport chain. But the end acceptor of electrons is not going to be oxygen. It's going to be reduced oxygen. So what will they use? They need an electronegative atom to be able to accept those electrons that they hand off. That's what they produce. Is that a socially acceptable thing? Not so much. What else do they produce? Cows produce a lot of this.
Nothing.
Yeah, that's the other thing, because you're able to shift electrons to either sulfur or carbons and making these fully reduced molecules. Now, the other problem with lactose intolerance is that lactose are these carbohydrates with all of these rich polar groups on them. So what are they going to bind? Water. So what you're going to have here is what's called an osmotic effect with a dramatically increased amount of water that's going to remain in the gut. And that is going to lead to watery diarrhea. And so that's the mechanism that leads to the gas and watery diarrhea for those that are lactase deficient. Okay, so now we've got our lactose digested into glucose and galactose. We have our starch, our amylose digested by amylase. Now, amylase is able to digest by hydrolyzing at these alpha-1,4 linkages. So all it's going to do is amylase is going to add water across this bond and break those carbohydrates off one by one. Now what happens when it gets to this break, when it gets to this branch point? The amylase, remember, is specific for this alpha-1,4 bond. The alpha-1,6 bond is not recognized by amylase. So that means we need another enzyme. That enzyme is going to be what's called the sucrase isomaltase complex. And this is a two-headed enzyme. So if this is the membrane of the epithelial cell that lines the intestine, what we are going to have is an enzyme that has two functionalities to it. So this is located in the same place, similar place as lactase on that brush border level. We are going to have one level of isomaltase activity, and then the other part of the enzyme will be sucrase. So by this double-headed enzyme, it's only one polypeptide, we are able to digest the alpha-1,6 linkage in the branch structure of starch by the isomaltase enzyme. Once we do that now, we release the two polymers, and amylase can continue its hydrolytic activity and digest all of these polymers all the way down to glucose. So glucose is the only thing we're going to get from starch. The other part of the enzyme sucrase, will be digesting sucrose as it's coming through the intestine. So the sucrase isomaltase complex and the lactase are the only two enzymes that are going to be involved in digesting our food molecules, getting these down to their individual components. Now, this is the principle of our digestion, getting our components down to the individual units. So with starch, we need to get to glucose. With sucrose, we need to get to glucose and fructose. With lactose, we need to get to galactose and glucose. We do not have any transport capabilities in our intestine to take up starch, sucrose, or lactose by itself. We have to get them down into their base units. And we're going to see that theme over and over again.
What were the three again?
Starch, sucrose, and lactose. So those are the three main carbohydrates that you have to know. And then when you break them down, the starch is broken down to glucose, sucrose is broken down to glucose and fructose, and lactose is broken down to galactose and glucose. So now what we have are our three sugars here. Our three monosaccharides. Here's our lumen of the intestine. So now we have to take these up into the body. So remember, on each one of these intestinal epithelial cells, we have tight junctions that form that impenetrable barrier between the lumen of the gut and the inside of the body. So that means that none of these sugars, none of these monosaccharides are able to penetrate what is called pericellular transport. They have to undergo regulated transport. So how do we do this? The first thing we'll talk about is glucose. Because quantitatively, if you think about our diet, think about how much starch you take in relation to sucrose and lactose. Starch is the major form of carbohydrate that we ingest. And so that means glucose is going to be the major monosaccharide. Glucose will bind to a transporter. This is a symporter, because this transporter requires the binding of both glucose and sodium ions. And once those two bind, then they can internalize both components inside the cell. This is called SGLT1 for sodium, glucose, transporter, isoform number 1. The other transporter that operates in the exact same function, the exact same mechanism, is called SGLT2. And that is located in the kidney proximal tubule. Now, I'm not very familiar with your renal curriculum, but did you talk about SGLT2? Okay, so I'll mention this briefly. What this is involved in is taking up glucose that is filtered through your glomerular complex. Because remember, the glomerular complex, that filter can filter out anything pretty much larger than albumin. So glucose being a small molecule, a lot of it might get filtered out through the kidney. So in order to prevent losing that glucose in the urine, there is a similar transporter on the kidney proximal tubule to take up glucose and put it back into the circulation. Do you think this might be a good target for anti-diabetic drugs? Yeah, because what this is going to allow you to do is to have an antagonist to this transporter, block its activity to try to regulate blood glucose levels by having your patients excrete it into the urine and get that blood glucose level down. So this is one of the hottest topics right now of developing pharmaceutical interventions in this point. Okay. So now, the SGLT1 on the lumen of the epithelial cell is going to be binding glucose and sodium and transporting them inside the cell. Now, you'll notice that we have a glucose/galactose here. Glucose and galactose are both hexoses. They're both 6-membered rings, and they look almost identical. In fact, they're epimers of each other. The only difference is the axial location of a hydroxyl group. You don't have to remember that part, the axial location of hydroxyl. But remember that these two sugars look almost exactly alike. And so that means that the SGLT1 has a little bit of promiscuity built into it, that it can recognize both of the sugars, and it can take up galactose and sodium as well as glucose and sodium. Now, fructose is very special. Fructose has its own transporter, and it's called GLUT5 for glucose transporter isoform number 5. Okay, why is it called a glucose transporter? Because the biochemists that isolated the glucose transporters made a horrible mistake. Glucose transporters, GLUT1, 2, 3, and 4, we'll go through all of them, are all glucose transporters. GLUT5 is specific for fructose. It cannot take up glucose, and vice versa, the other glucose transporters cannot take up fructose. Simply because, remember, fructose is a 5-membered ring carbohydrate. And so structurally it's very, very different, and it has its own transporter. Now, once we have our monosaccharides in the cytoplasm of the cell, we've got to get these across the basolateral surface and placed into the blood so we can have these available to us for metabolism. So glucose and galactose are going to be transported. Both of these are going to be transported by the GLUT2 transporter on the basolateral surface. And again, this is the glucose transporter, isoform number 2. You'll see fructose also goes by GLUT2, This is something that is in the textbooks, and it may actually be in first aid. I forgot if it's in the newer version. This is incorrect. Fructose has a GLUT5. Because the GLUT2 is specific for glucose and galactose. We cannot recognize that 5-membered ring. So that path is incorrect. This is going through GLUT5. Now, how do these transporters work? We have to have energy. Glucose is our primary energy source, so it's very important that the body take up every little shred of glucose. So what we're going to do is we are going to put a sodium-potassium ATPase transporter on the basal surface of the intestinal epithelial cell. This is going to harness ATP hydrolysis to drive the transport of sodium out of the cell, potassium in. What this is going to do is it's going to decrease the concentration of sodium inside the cytoplasm of the cell. By doing that, we now have established a concentration gradient of sodium that is high in the lumen, low inside the cell, and so now this concentration gradient is driving SGLT1. And in doing so, glucose and galactose are piggybacking on here. So it's the power of this sodium-potassium ATPase transporter that's driving this whole mechanism. Because we need an active method to get that glucose inside our cells. Now what about fructose? Fructose is only operating through facilitated diffusion. So that means that the GLUT5 transporter, and actually all of the GLUT transporters, 1 through 5, are operating on a chemical gradient of fructose being high in our diet and low inside the cytoplasm. And this is kept low because of the GLUT5 activity to put this into the blood. So fructose, not being the most important carbohydrate for energy, is only being taken up in the body by facilitated diffusion. There's no active transport. So this is really important, this principle, when you're trying to convince your patients about diet modification. If you consume glucose and galactose in any form, you have very powerful active transport. Fructose, the transport of fructose from the gut into the body occurs by concentration gradient. So if you decrease the concentration of fructose in your diet, you are going to dramatically reduce the amount of fructose that gets into the body that leads to fat development. And so this is why there's a huge push right now to get those high fructose corn syrups out of our diet. Is because this particular sugar, you can control the uptake because it's concentration dependent. The uptake of glucose, no way. This is primary active transport. We cannot control that because glucose is so important to us. Okay. Now, how do you use this information for your personal benefit to cure a hangover? Actually, it's more important that you know what your patients are using for hydration therapy. So, here's our lumen of our intestine. Here's our basolateral surface. This is the blood. And this is how those hydration sport drinks work. The hydration sport drinks will have a combination of sodium chloride and sugar, sucrose. We have our sodium-potassium ATPase transporter that's powering all of this to push the sodium out into the circulation to decrease the concentration of sodium inside the cell. We have our sport drink Coming down the lumen, at this point, we now have sodium chloride. Assuming that it's sucrose, we have glucose plus fructose. And so this ATPase transporter is now able to drive the glucose in along with the sodium using SGLT1. And what does water do? Always in the body. It's going to follow the ions. And so that's why these sport drinks are so popular, because you're supplying the mechanism to get these ions and these osmotically active molecules, the carbohydrates, and then the water in your gut is going to flow in to hydrate the tissue. Now, the reason I bring this up and emphasize it is because we now have what are called diet sport drinks. And your patients might say, well, I'm going to use this instead because there's 0 calories, because there's no sucrose. Will a diet sport drink really serve in hydration therapy? No way, no how. Because these artificial sweeteners are not metabolized by the body and not taken up. And so if you do not have the glucose available, you may have the sodium available, but this transporter will not work unless both glucose and sodium are bound to it. Yes?
Do you mean glucose plus fructose, or do you mean glucose plus galactose?
For this, if this is sugar being sucrose.
Okay.
If this is just sucrose, it's going to be glucose and fructose. And what we're interested in primarily is that glucose.
Okay.
So that's why having actual sugar in the drink is important, and the diet's drinks will not work because you can't get these ions and sugar flowing through this membrane.
So the SGL1 is just for the glucose.
Just for glucose.
In that case.
In this case, right. Also, we'll have galactose. Maybe some of the sport drinks might have some galactose in it. Now, why don't you just have a sport drink with sodium chloride and glucose in it? That'd solve the whole problem.
It tastes pretty gross.
It would taste pretty gross. I've done this in the lab. I've been curious. I got buckets of glucose sitting on my on the chemical shelf. So it's like, taste this thing? Yeah, it's nasty. It's just, it doesn't have that sweetness. Fructose, yeah, I know, I sampled my work. I have not drank a beaker full of H. pylori, though. That's just, I draw the line somewhere here. Okay, so we're good with carbohydrate digestion and uptake. So now at this point, we have these molecules, glucose and galactose and fructose are major carbohydrates. We now have these in our circulation. So now, at this point is when we begin metabolism, which will start on Monday. So what about proteins? So here's protein degradation. Very easy. You know all this. Protease-mediated hydrolysis. So we have our protein down here. Beginning of digestion starts in the stomach with pepsin activity. The majority of digestion is going to happen in the intestine because of the pancreatic secretions. And simply all these enzymes that are going to digest the protein, what we want to specifically do is hydrolyze the peptide bond. And by doing that, we are generating amino acids. And amino acids are what we are capable of absorbing inside the body. So same principle as carbohydrates. Take the large molecules, break them down into small individual components for uptake. Let's see if I can zoom up on this. So how do we digest proteins? Well, we sense proteins, we put out the hormones, specifically CCK, stimulates the myoepithelium of the exocrine pancreas, pushes out and increases secretion of the proteases. And these proteases are coming out of the pancreatic duct. And remember, these are all in the form of zymogens. So zymogens are the inactive form of the proteases. And they're designed this way and secreted by the pancreatic cells because if they were active proteases, you could autodigest the pancreas, leading to pancreatitis. So the pancreas is going to protect itself by secreting these zymogens. Now, what terms are for zymogens? Well, look at these lists right here. We have trypsinogen. So whenever you see the ogen, such as that, chymotrypsinogen, that means it's a zymogen in active form. Proelastase, if you have a pro designation in front of the protease name, that's also a zymogen in active form. When you see these are not able to digest proteins. They have to be activated. So how do we activate these? We want to activate them in the location where they need to be used, not in the pancreas. All of these enzymes are capable of auto-activation. So they do not necessarily need this mechanism, but this mechanism accelerates their activation because you want to accelerate it in the intestine with the food products. They auto-activate in the pancreas if what doesn't occur? What's the hormone that helps secrete and wash? Secretin, yeah. So if secretin isn't doing its job to push out the bicarb and push out the water from the ductal cells, these enzymes are going to sit in the pancreatic ducts for too long, and they'll start auto-activating, and then you've got active proteases. So what happens when the inactive forms get into the duodenum? Well, we have the beginning. It's this protease that's located on the luminal surface of the epithelium. It's called enterokinase. This is an absolutely horrific name. Why is this such a bad name? What does kinase indicate to you? Phosphorylation. Yeah. This enzyme has absolutely no kinase activity whatsoever. You can blame the biochemists. Those people, I'm telling you, they mislabel things. Oh, it's terrible. I didn't do it. This is before my time. So enterokinase is an activating protease. What enterokinase is going to do is it's going to take trypsinogen and it's going to activate it by enzymatic cleavage of the trypsinogen to active trypsin. So the activation is very simple. I like drawing enzymes as Pac-Man, or Pac-Lady, Miss Pac-Man. Gotta be gender neutral with Pac-Man. Here's the active site of your Ms. Pac-Man. Your protein comes in, and what is supposed to come out are amino acids. Here's the function of the protease. What an inactive zymogen is, looks like this. It has a small piece of protein that covers the active site. So the protein cannot get into that active site. What the enterokinase is doing to trypsin is it's cleaving that site. It's actually performing a proteolytic cut to release this peptide and now opening up the active site of trypsin. What trypsin then does is it goes out and now activates all of the other proteases. So it's a cascade effect. So now we have all of our active enzymes. So with these enzymes, these particular enzymes in their active forms, What I have found so far as what you need to know, is that you need to know about the enterokinase activation system. You need to know that it activates trypsinogen, the zymogen, into the active form of trypsin, and then trypsin catalyzes the activation of the other proteases. As far as knowing what these proteases do in their names, I've not seen any examples of that. I don't recall seeing it on step 1 or first aid, and it's definitely not in our database of questions for this block. What is important to know is that there's 2 types of proteases. One is an exoprotease. That means if you have a protein that is N and C terminus, the long polypeptide, the exoproteases will work at the ends. The endoproteases will digest the protein in the middle. And if you digest the protein in the middle, you create 2 brand new ends for the exoproteases to work on. And so you can see the key element on knowing endo and exoprotease, that you can digest the entire protein very rapidly, so you're not limited to just the ends. You can keep creating ends. Okay? Good so far? Okay, so now we've got our protein digested down to amino acids. So how do we get the amino acids into the body? It's the exact same mechanism as the glucose transporters, SGLT1. We have amino acid transporters. Large protein meal, sometimes these proteases are not completely efficient. So instead of taking the protein down to amino acids, we're going to digest the protein down to di and tripeptides. We have transporters that can take the di and tripeptides up into the enterocyte. And then we have the enterocyte contributing intracellular peptidases, intracellular proteases, to complete the digestion of those di and tripeptides into amino acids. And then what comes out into the blood, again, are amino acids. Why do we want to make real sure that we're only putting amino acids and not peptide fragments in our blood?
Peptides can cause immune reactions.
Can cause immune reactions, right? So remember back when Dr. Chakarian was talking about antigenicity, you can get down to a peptide around 9-10 peptides long that can elicit a very powerful immune response. And so that's why we have this dual mechanism to make sure that it's only amino acids coming into the blood. We also have another system, backup, for large peptides. So if we have peptides that are, say, maybe 20 or 30 amino acids long, assuming our normal proteins are 200, 300, 400 amino acids, we have what are called brush border proteases, or brush border peptidases. And these are proteolytic enzymes that are actually in integral membrane proteins on these microvilli structure to just allow a little bit more digestion. Now you can see from this why that segmental contraction is so important. Segmental contractions are mixing all of these enzymes with the chyme, with the food material, to make sure that you've got good surface exposure of the enzymes to all of its substrates. But also, you need to mix this material up to get it near the surface, the absorptive surface, so that these transporters can work. So that's why the segmentation contractions are so vigorous. Now, on this drawing here, I show amino acids. Transporters have levels of specificity. SGLT1 will work on glucose but not on fructose. What about amino acids? There's 20 of them. They all have different structures. We do not have 20 transporters. What we have are class-specific transporters. So some will recognize neutral amino acids, others will recognize basic, others will recognize acidic amino acids, and there's also transporters that will recognize phenyl groups on there, like tyrosine and tryptophan. So we have class-specific transporters. Now, do you have to remember what all the 20 amino acids are and which transporter that they have to? You're all saying no, so okay, no. I can be influenced. Yeah, no, you don't have to know that. Just know that there's class-specific different transporters that are responsible for taking up each one of the classes of amino acids. Okay, good so far until we move on to fats. So we talk about fats in our diet. What do we mean by fats? These are the primary fats in our diet. The major lipid in our diet are triacylglycerols, also known as triglycerides. We're going to be going more and more into the structure of these and how the body handles them as we progress. But I'll continue to say it's a chemistry problem. And here's the reason why. Here's the backbone of a triglyceride. It equals glycerol. So remember, glycerol is a 3-carbon unit and it's got hydroxyl groups, OH groups on each one. What we're going to do to these hydroxyl groups is we're going to add a long fatty acid chain. And remember, the fatty acids have a carboxylic acid on one end, and it's a long hydrocarbon chain. Very, very lipophilic. We're going to put 3 of these on that glycerol backbone, and this is our base structure of our triglyceride. Our body cannot take up triglycerides in the intestine. We have to do the same principle that we've done with carbohydrates and protein. We have to break this molecule up into its component parts, and then we'll have transporters available. Here's our cholesterol molecule. We know we get that in the diet. We'll talk more about this in pharmacology of cholesterol management, but there's a transporter called NPC1-like1. I didn't name it. I would never have named it that way. I'd call it a cholesterol transporter. It actually comes from Niemann-Pick disease. NPC1L1. This is the transporter in the intestine for cholesterol. We'll talk more about that when we talk about pharmacology, because this is a wonderful target for anti-cholesterol drugs. The other one are cholesterol esters. Cholesterol esters are simply cholesterol with that number 3 hydroxyl group attached with a long chain fatty acid. So this designation is a carboxylic acid. This is an ester linkage. And we are going to add this R group, which is that long hydrocarbon chain, just like we have on triglycerides. So that's a cholesterol ester. You can imagine that thing is 100% lipophilic. And then the last fat in our diet are phospholipids. Phospholipids, again, also similar to triglycerides, they have a glycerol backbone. But and different from the triglyceride, we have 2 fatty acids attached, and here we have a head group. And this head group is typically charged or polar. So when we draw our membrane structure, we draw our fatty acids like this to draw our lipid bilayer structure. Remember that? This head group represents the circle, which is the charged or polar domain that faces the aqueous environment. And these fatty acids represent the tails. And so that correlates that structure with the phospholipid. So how do we handle lipids? This is where we go back to bio. So CCK is allowing the push of that bile out of the gallbladder, and the purpose of bile is to do this particular reaction. Our large lipid droplets. When I was in my freshman year in high school, my good friend, we were sitting there having lunch together, and he had this thing about fats. He would not eat fats, and he took one of my potato chips, and he ground it up in his hand into a pulp. And then he said, "Look at my hand, and you're going to eat that." I hated him ever more. Potato chips. So what are you seeing on there? Fat droplets. All of those little lipid droplets on your hand from all that fat. Well, that's exactly what it looks like in your intestine. So you've got these really large fat droplets you got to break up, primarily to increase the surface area of the droplets so that we can process them. And that's what the bile does. The bile mixes in here, and this here is the process of emulsification. Emulsification is not a chemical modification. We're not doing any kind of modifying of bonds, covalent bonds. All we're doing is we're taking the bile, and the bile is wiggling its way inside these lipid droplets in order to break them up into these components. Now at that point, pancreatic lipase is able to start digestion. Pancreatic lipase is going to be digesting the triglycerides. What we are going to take is our triglyceride, is our glycerol backbone with our 3 fatty acids. And we are going to start cleaving off of these fatty acids. So the lipase is just simply going to hydrolyze that ester linkage. Yes? Oh, sorry. Yeah. Hydrolyze off the fatty acids. It's going to take off the first one on one side, hydrolyze off the second one, and what we're going to end up with are 2 free fatty acids and 2 monoglyceride. And so the 2 monoglyceride structure is simply this triglyceride with the number 1, 2 fatty acids still intact. So these 2 fatty acids on the ends are being removed by the lipase activity. Now once we have those these activities, these 2 hydrolytic cleavages to generate these 2 products, now we have a mechanism to take that up. Here's another description of what's happening. Our triglyceride, we're removing this fatty acid, that fatty acid. I should draw it that way, be complete. And then we're left with that 2 monoglyceride structure and our 2 fatty acids. Now you'll notice this little thing called procolipase. The lipase is secreted from the pancreatic acinar cells in the same inactive form as the proteases are. The pancreas also secretes colipase. The prolipase is activated into colipase by trypsin that has already been activated. The colipase now works in conjunction with the lipase enzyme to do this hydrolytic cleavage. The reason for that is for the same purpose of protecting the pancreas. A lipase in the ducts of the pancreas, although it has very low affinity for phospholipids of the membrane, you could start getting pancreatic lipase cleavage of the phospholipids of the ductal cells, and now you've got pancreatitis, pancreatic damage. So this colipase is the mechanism of keeping the lipase inactive until it's needed in the intestine. Okay. Now, cholesterol esters are the same thing. We have cholesterol esters. We cannot take up cholesterol esters. We need to break it down into its units. We have cholesterol esterase, also called cholesterol ester hydrolase. The common name is cholesterol esterase. And that is simply going to be removing the fatty acid that is attached to here to release cholesterol and the fatty acid. The cholesterol, of course, can be taken up by NPC1L1. We'll talk about that later. And the fatty acid can be taken up by this mechanism. So taking up fatty acids is done by facilitated diffusion. There's no active transport of fatty acids. What we have are these molecules, FATP, and that stands for fatty acid transport protein. Once the fatty acid binds to this transport protein, it's translocated across the protein and into the cytoplasm. And here is where you'll see your first biochemical reaction. Because this is facilitated diffusion, it's not active transport, we have to prevent the reverse transport of fats out of the cell. And the way we're going to do that is we're going to trap the fatty acid inside the cell by using an enzyme called fatty acyl-CoA synthetase. What this is going to do is it's going to add an acyl-CoA structure. So now what we're going to have is a fatty acyl-CoA. We'll pick this up in metabolism, but for now, just notice that fatty acyl-CoA is not the same structure as a fatty acid. And so this transporter cannot recognize the coenzyme A derivative. So that traps it in there. Now I've got here passive diffusion versus protein-mediated transport. This will become important again as we're building on fatty acid transport diseases. Short and medium-chain fatty acids can pass by passive diffusion. Passive diffusion is simple diffusion. Because these are soluble in the membrane, they can pass through the membrane without need for this transport structure. So now we have these fats in the cell. We have 2-monoglyceride and fatty acids, and we have cholesterol. We have them all broken down to absorb them. They're all broken down inside the cytoplasm of the enterocyte. Now, we cannot take cholesterol and free fatty acids and put it into the blood. That's just not going to work because it's a chemistry problem. So we have to package the fats up special to be able to transport them. I'll give you the punchline. The punchline is right here. Chylomicrons. Chylomicrons are a form of lipoprotein. We will go into excruciating detail on all the lipoproteins, but we'll start with this one because this is a dietary lipoprotein. What we're going to do now is we're going to take all of these molecules, these free fatty acids, 2-monoglyceride, cholesterol, everything that is coming inside the enterocyte, and we are going to repackage them. The first step we're going to do is we're going to perform what's called the monoglyceride acylation pathway. Very simple. We are going to take 2-monoglyceride. We are going to add 2 fatty acids to this, and we are going to generate a triglyceride structure. So we're reassembling exactly what we just broke down. The cholesterol, we are going to what's called esterify. And this is simply taking that fatty acid that we just cleaved off the cholesterol ester in the lumen and put it back on the cholesterol. So we're completely reversing what we did in the lumen. Now, once we have the triglyceride and our cholesterol ester, now we've got the building components to put this system all back together again. The first thing we need to do is we need to have a scaffold. And that scaffold is going to be a very large protein that is synthesized by the enterocytes. And this protein is called ApoB 48. And that stands for apolipoprotein B48. This protein is going to be the scaffold or skeleton of the chylomicron structure. So now, we'll take the triglycerides, we'll take the cholesterol esters, and we are going to attach them to the protein, ApoB 48, in a non-covalent fashion. So the way I like to picture this is the protein is going to be like a serpent. Picture the triglyceride and the cholesterol esters coming together into a core, and the protein is going to be a serpent in and out of this lipid droplet that we're forming. What that will do is allow us to secrete the chylomicron out of the cell into what is called a soluble form for lipid transport. Now, the particular enzyme that assists in the construction of this chylomicron is called ACAT. And that stands for acylcholesterol acyltransferase. So this enzyme is located in the endoplasmic reticulum, where the protein is being made, and it is going to facilitate the transfer of triglycerides and cholesterol esters as that protein begins to fold. And then that will make the chylomicron structure. Now, chylomicrons are huge. These things are approximately 500 nanometers in diameter. So if we secrete this outside the cell, this size will not enter a capillary. Because remember, the capillaries in the gut, the mesentery, they don't have a lot of open junctions between them. So material would have to percolate between those cells. The junctions between two endothelial cells is anywhere from 20 to 50 nanometers in diameter. Our chylomicron is 10 times that size. So they do not enter the capillaries. They enter the lymphatic system. And so the lymphatics, they all collect into the thoracic duct. And that empties into somewhere around here. It's the right subclavian. Good. Right subclavian vein. So all of the mesenteries that drain the lymphatic system all go into the right subclavian from the thoracic duct. At that point now, the chylomicrons are in the circulation. And so now they're soluble in the blood, they can transport in the blood, and they can deliver this fat to the needed tissues. So now we've got our carbohydrates, we've got our proteins, and we've got our fats, our lipids, inside the body. So now at this point is when metabolism begins, because now we are going to extract these molecules and we're going to start doing something with them. But the body has to be able to tell that there's these fuel molecules out there, and that's where we'll pick up with the physiology on Monday. Last thing to mention is that I put this up here in your notes to remind you of the nomenclature of fatty acids. I'm not interested in you know that this is C18 is stearic acid, C18-1 is oleic acid. What I'm more interested in is that you know the nomenclature of a fatty acid so that the carboxylic acid carbon is number 1. We number toward the methyl end. This is the omega end. The number 2 and number 3 carbons are alpha and beta. And that's going to become real important when we process. So if you've got a fatty acid that is 18 carbons long, fully saturated, no double bonds in here, it's designated as 18:0, meaning 18 carbons, no double bonds. If you have a fatty acid that is 18 carbons with 1 double bond, starting at number 9 carbon, 9 counting from this carbon first here, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 18 carbons, 1 double bond, delta 9, indicating that this double bond starts at carbon 9. That is step 1 information, believe it or not. And I think the reason it is because as physicians, these are the 2 fatty acids that you'll be dealing with most. Omega-3s and omega-6s. And these designations are simply where the double bond is located, counting from the omega end of the fatty acid. So here we have 1, 2, 3. Double bond starts at carbon 3 from the omega end. That's an omega-3. Likewise, 1, 2, 3, 4, 5, 6 double bond. That's an omega-6. Why is that so important for you? We're going to go into this in much greater detail in a few weeks when we talk about eicosanoids. But these omega-6s are the backbone and substrates for synthesizing the inflammatory lipid mediators. So this is the problem with your patients that have arthritis. They come to you and say, you know, I've been hearing on television that I should take more omega-3s. This is why. If they take more omega-3s, they can tip the balance and add more anti-inflammatory lipids into their system to depress the synthesis of the inflammatory. And that's the basis of the omega-3, omega-6 discussion for anti-inflammatory therapeutics. And we'll go into that in much more detail in that mechanism later.